Hi, and welcome to CodePaper. My name is Malia, and I'm here with my teammate Murphy, and today we are thrilled to show you our capstone project, CodePaper. CodePaper is an interactive exhibit that was created for ScienceWorks and is located inside the robotics room. This open source project was first inspired by Dynamicland, and we wanted to revive the outdated version of this software and introduce an augmented reality component. To begin, I want to provide a brief look at our agenda. First, I'll be talking about the importance of play and how this influenced our project. I'll then transition to the motivation for CodePaper, along with some major features, requirements, and the tools needed to create the project. Afterward, we'll be showing a brief demo of the exhibit, and then Murphy will talk about some of the challenges we faced, along with the testing we completed to overcome them. We'll also talk about our division of labor, possible expansion for CodePaper, and then concluding remarks. So without further ado, the importance of play. Play is imperative for early education, as it's a child's innate sense of learning. For instance, toddlers may learn their colors by playing with bright blocks. Grade schoolers may learn to count by jumping rope, and high schoolers may learn anatomy by using Kahoot. As you can see, play comes in all shapes and sizes, and it's important to have play in the learning environment, as it encourages kinesthetic learning, as opposed to a didactic form of education. Studies have even shown that play in educational settings can improve cognitive, physical, social, and emotional well-being. So, when reflecting on CodePaper, we knew that we wanted to ensure that each child was using play as their primary form of learning while using our exhibit. Which brings us to our motivation. Our primary goal was to provide ScienceWorks with an exhibit for the robotics room. For those of you who are unfamiliar with ScienceWorks, it's a local hands-on museum where children are encouraged to explore many interactive exhibits. This gave us a unique opportunity to create an exhibit that introduces children to computer science while still utilizing play to make discoveries. It's also our hope to increase diversity in STEM by immersing children from many different backgrounds into the fascinating world of STEM exploration. In order to make our goals a reality, we knew that CodePaper would need two major features. The first is to run continuously during museum's operating hours, and the second was to provide an interactive and educational experience. Now, although there are only two major features, each feature is broken down into sub-features. So first, I'd like to talk about running continuously during museum operating hours. In order for this exhibit to run successfully during the day, we wanted to make sure that it could do three main things. First, that it could start very quickly and easily. The second is that the calibration would be automatic, and that it would remain running. So, first, the simple setup. When we first started this project, it took a lot of work for the program to even be able to run. The software required a lot of terminal commands, and it just took too much time. So we optimized this and decreased the amount of commands it would take to run this, and you can also run it inside the command line, which means that the museum operators will need to spend significantly less time to start this each morning than before. Along those lines, we also added automatic calibration. This allows the cameras to see the dots on the paper and reduces the time that the museum staff would spend on calibrating each color manually. Our last feature is that it needs to remain running during museum operating hours. The hours are from Wednesday to Sunday, 10 a.m. to 5 p.m., and we want to ensure that no matter what may happen to the exhibit, that it'll remain on and running. So if a kid bumps the table or removes all of the papers or puts on too many papers, we want to make sure that no matter what may happen, that our exhibit will continue running. And those are our first major features. And our second major features are going to deal with providing an interactive and educational experience. Providing an interactive and educational experience with our exhibit requires 8 core sub-features. The first of these is to display a maze. So CodePaper actually uses a projector and a camera to display and read information in parallel, and this is what allows the exhibit to remain interactive. CodePaper also uses a default configuration. So this is what shows when the exhibit isn't being used. So when a user walks up to this, they can understand that the exhibit is running and waiting on user input. The next feature that we have is executing an algorithm. CodePaper uses algorithms to visualize pathfinding, and users can actually place one or multiple algorithms at the same time to be able to see that path in live time. And with this, we need a dynamic response. So CodePaper continually monitors state changes, and this allows users to move their papers and receive an immediate response. And with that, we can actually introduce the ability to block. CodePaper has these blocking functionalities that allows users to choose an area of their path where their finder can't access. And this can trigger special events. And we want children to be able to explore the capabilities of the exhibit and have a fun journey of discovery. And so we're not going to tell you these because we actually want you guys to go and use our exhibit and see what some of these fun little features might be. Another main sub-feature that we have is a response to minor movements. So we found that when children would come up to the exhibit, they might bump or push a paper just a little bit when they're not actually meaning to move it. So we made sure that our exhibit wouldn't respond to these minor movements, but would respond to major movements. Our last feature is that our exhibit includes multiple languages. In our efforts to include diversity in STEM, we made sure to include all of our paper instructions in both English and Spanish. And we're hoping that this is able to allow more children to be able to use this exhibit. So here's a comprehensive list of all the tools and technologies we used in order to make CodePaper successful. And you can also see a cute little diagram of this. And I encourage you to actually go and visit ScienceWorks so you can see this setup in action and kind of get a better understanding of what's going on now that you have a little bit of behind the scenes. But in case you can't go, we'd like to show you our demo. Hi, and welcome to ScienceWorks. Today we are thrilled to present a demonstration of CodePaper. CodePaper is an interactive exhibit that was created for ScienceWorks as a part of Southern Oregon University's capstone projects. Our exhibit is located inside the robotics room, and as you step inside, you'll be greeted by a fusion of cutting-edge technology. To our right, we see our CodePaper exhibit. This open source project was first inspired by DynamicLand, but we wanted to revive the outdated version of this software and introduce an augmented reality component. The exhibit uses various tools to transport children into an exciting learning environment. As we saw, the exhibit is already running when you enter the museum. This is our first major feature, and it's important as we want to ensure that CodePaper can run all day. So, a lot of the work is being done behind the scenes by this computer, which is located behind the exhibit. We also used a projector and a camera mounted above the exhibit to capture user input and project it to the table's surface. So, let's dive in and discover what makes this exhibit truly extraordinary. Here we see our second major feature, which involves an interactive display. This is designed to engage the museum's visitors. When the camera, projector, and paper work together, you can uncover hidden details, trigger dynamic events, and unlock a world of discovery, giving children the power to shape their own journey.
Next, we'll introduce how the exhibit works. When you first walk up to the table, there are start and finish points present. This is the default configuration, and this feature ensures that each child will already have an idea of what to do when they walk up. Then the children can use the papers to select which algorithm will be used to find a path from the start to the finish. We will first be demonstrating executing Dijkstra's algorithm, which tells the Pathfinder to find the shortest distance from the start to the finished points. This is done by looking at each adjacent square and expanding outward until the finished point is found. It then calculates the shortest path using this information. Here you can see where Dijkstra's algorithm is expanding toward the finish point represented by orange squares. However, children can actually put multiple algorithms on the surface at once, demonstrating the difference between the algorithms. We use A*, an optimized version of Dijkstra's algorithm, to show this. Like Dijkstra's, A* finds the optimal path, but it does so more quickly by considering where the finish point is, thus exploring fewer squares. Similar to showing Dijkstra's path using orange squares, the A* algorithm is represented by blue squares. However, if both algorithms have looked at the same square, we represent this with a triangle pattern. Another important part of this feature is dynamic response to input. For example, if you decide to remove an algorithm, it will automatically update the projection surface. Children can also use the dynamic response feature to be able to change where they want their maze to start by placing a start paper anywhere on the projected surface. The maze finder will restart their search. And of course, you can't have a start without a finish, so the children can also use this dynamic response feature to place a finish paper, telling the maze finder where the path terminates. Another aspect of this feature is the ability to block a path by adding obstacles. When a user places this piece of paper, it tells the Pathfinder that it cannot go through these points, forcing the maze to find another route. This exhibit encourages discovery, so there are even special events that get triggered if a user is able to completely block a path. This exhibit also ensures that minor movements of the paper will not interfere with the projected events. In our efforts to increase diversity in STEM, we have included Spanish versions of each of the papers.
And there you have it, our interactive exhibit engineered to propel children into a world of STEM exploration. Thank you for joining us on this preview of CodePaper. We look forward to welcoming you to our exhibit.
For paper testing, so we had to test if there's no papers present, what would be the default configuration for it. If there was none, one, or multiple algorithms present, one, neither, or both start and finish papers present, none, one, or multiple block papers present. So this ensures that any combination of papers there or not there will always have the desired output. For projector and camera testing, we tested using laminated paper. Since children will be using this, we didn't want them to shred the paper up or crumple it in some weird ways. For changing dot sizes, we tested with getting bigger or smaller dots, but it found out that having bigger dots actually led for our software to be able to recognize them much easier. For changing the grid size, so changing actually the size of the squares, we did test having less than what are there now, and we found that it actually propagated so quick that you couldn't even tell what was going on, versus having really small ones, it actually took way too long. So we found about where we're at now is a good sweet spot. Lastly, testing in a new environment, which will be talked about later in the challenges. For path testing, making the endpoint unreachable, covering the start and end points, and also running blocks with multiple algorithms. An issue that we had that was found through testing was that both algorithms were actually influencing each other, so they were fine on their own, but as soon as you put two and two together, with blocks running specifically, there was some errors that were happening. So that was an important piece of our testing. So now we'll be talking about challenges. So first was preloaded programs. So initially, the project had some weird file system where everything was stored on the cache. So we made it that we can store it separately and actually be able to access it from different computers at different times, and then be able to load that in when a browser is open. Another challenge was algorithm implementation. So this included Dijkstra's algorithm, A*, and then also getting it to look correctly on the projected surface. New environment deployment was a challenge just because our CS lab and ScienceWorks, although they were similar, there was some key differences with the lighting and whatnot and being able to calibrate. And also this really included ScienceWorks being able to get the exhibit up and running every day quickly because they got to open the entire museum inside of 30 minutes. So, and then lastly, most of the work that we did last term was performance related. So having a satisfying feeling of moving the papers around was something that was a big challenge and I think could still be improved upon. For division of labor, implementation was a huge part of this term. Malia and I both split it half and half, and documentation took a little bit of a smaller role versus last term. So for implementation, A* was implemented by Malia, and then I did Dijkstra's and more of the grid line setup. But both of us had a pretty even split for the work that was done this term. Some expansion for CodePaper, so next term, further performance boost to improve the augmented experience. So, and then that kind of leads into the implementation of games such as Pong and Brick Breaker. We had a little bit of a delay, which is why our values aligned with ScienceWorks with creating MazeBot. Lastly, having ScienceWorks customers being able to write their own code is another interesting idea for next term, with maybe they have MazeBot, but instead of our algorithm solving it, they create the algorithm for solving it, which would be a fun play with computer science and also some learning opportunities. So the strengths of our project is the ability to expand the exhibit by further incorporating games and activities, and then also being able to respond to paper movement in live time. Some uniqueness of our project would be for that CodePaper utilizes play to encourage children to learn by using real-time visualization. And also, CodePaper is a hands-on approach to early education and coding. I think this was also a unique opportunity for us for having an exhibit go into ScienceWorks is a unique opportunity, and also we are very grateful for that opportunity as well. Last, the impact that CodePaper can have. CodePaper acts as a tool to redefine the introduction process to programming for children. being able to have an exhibit that at least introduces children to algorithms and STEM is a great impact for the future STEM students of tomorrow. And then CodePaper can also increase diversity in the field of STEM through early exposure. I think this quote best explains the heart behind our project. So games aren't just filler and education. They have the ability to introduce, reinforce, or even assess learning of a given topic. So thank you guys for listening to our presentation on CodePaper.